Next up, Simon Bazelet will be discussing cancel, retry, and timeouts. Tell us how reactive programming can help us keep our sanity, Simon.
Hey everybody. Thanks for joining me today for this session on cancel, retry, and timeouts, how to keep your sanity thanks to reactive programming. Today I'm going to talk about these three topics from both an imperative perspective to compare with the reactive approach and what it can bring to the table. It will be a mix of slides and a bit of a code demo. But to talk about these subjects, these topics, I would take the example of the infamous request response. So first, let's have a look at how the request response in kind of an HTTP context works when you are dealing with an imperative and blocking world. Well, you just make a request with whatever client of choice you have, and you receive directly a response. But if you, as the user making this request, if you notice that there is some latency, and there's bound to be some latency, but if you notice that the request take a bit too much time to execute, there's nothing you can do really. You still have to wait for this response to come. So once you've made the request, you are blocked waiting for the response. You cannot really cancel it because the only thing that you have is in your code from a developer perspective is a call to this client.makeRequest method, and then a response object that execution won't resume until this response object has arrived. So that's the imperative blocking world. You cannot really cancel in the blocking world. I was going to do a quick demo, but I don't think it's really that interesting before we switch to the synchronous world. So what can you do to alleviate that? You want to be able to cancel, like let your users in the app cancel a request if it takes too long, if they perceive it takes too long. But in a blocking world, you cannot really do that. Well, you could switch to asynchronous, and the first way to turn to your code into asynchronous code is to use a future. So maybe you can find a client that represents the request and response as a future. So you make the request, but you get a future of a response. And so if your user notices that there is too much latency, they can click on the button stop, and you will be able to cancel that request. And you do that because there is on the future object that you got immediately, there is a cancel method. So it's great. Let's see that in action. So here I have an application. It's a Java FXML application. It's not terribly interesting, the details, but I have, if I run that, I have a way to simulate a request and choose between blocking and future-based tasks. So here I have the code for the future. So I have my client. I make a request in the form of a future. Actually, I have a little wrapper here that allows me to display it in a graphical way. But the real gist is that when I trigger the actual request, I get a completable future. and I can detect when it's cancelled. I can detect when it's completed, where it's failed. I can update the GUI accordingly. But more importantly, I have a cancel button, and it will detect if my currently running request is a future. If it's a future, it simply calls cancel. So let's have a look. So that's the app. Very, very simple. If I select future and I trigger the request, it loads. Okay, takes about 3 seconds to execute. So you notice here I have this cancel button. So if I run it, I cancel the future, and I see that my second future request was cancelled. If I were to switch to blocking, it would be bad because, hey, maybe you saw that little loading cursor. The whole UI is actually blocked because it's executing inside the UI thread, and it's blocking the UI thread for 3 seconds. So it's actually freezing my my app. That's bad coding practice on my part, but it demonstrates that you cannot cancel, and it's really a blocking behavior. All right. So let me close that for now. So we see that we have the possibility to cancel. The future is more or less straightforward. So we do have to cheat a little bit because completable future actually doesn't propagate the cancel signal when you compose and you cancel the outermost future in your composition. It doesn't propagate the cancellation to the innermost. So here we have to cheat a bit. We have to take the future that our client gives us. We add it to this queue that will be used by the cancel button. And then for updating, like dealing with the result of this request, to updating the UI, namely, we compose on top of that work future. If I were to add this future to the queue, I wouldn't be able to cancel it. I can actually show it to you. So if I do that instead, oops. If I do work queue, add this feature instead, let's see what it does. It's taking a bit of time to start. Okay, here we go. Okay, so let's select future again and perform a simple request and try to cancel it. And you see that it's still like it has nothing to cancel in its queue, but it still progresses. So the request is actually it's actually still running. Okay, so we already had to cheat a bit for making the cancellation work with the future. So not great, right? So let's see. What if the request is more complex? like a sequence of multiple calls. With future, it would do something like that. Imagine you have to fetch a list of IDs from a remote endpoint, and then for each of these IDs, you perform an individual, like an inner request. And the code is already not that great, right? So we switch to completable feature. We use completable feature of a list of strings to represent the first step of fetching a list of IDs. And then we'll loop, and we would probably need to do that sequentially and check inside the loop, whereas the user, the user cancel the global request, the global process. But as long as it didn't cancel, then we make the next inner request. So we have something like that is more involved. So even if we trigger multiple inner requests, if it takes a bit too long, then you have to actually kind of programmatically cancel them one by one and keep track of every request. And as we saw, so canceling gets more complex, basically. As we saw, even with a simple request, we had to cheat a bit to propagate cancellation. So it's not that much of a, I'd say, a first-class citizen in the completable feature world. By the way, yeah, I know that this previous code can be made more lenient and turned into single completable feature with some combination operators, but it's not that. It doesn't bring that much value. So yeah, how do you kind of represent a complex sequence of steps, of asynchronous steps, and make sure that by canceling a single representation of this processing, you cancel every step that might have already started? This looks like a perfect case for mono, for a reactor. So in reactor, we would use a mono. We would have a first step that is represented as a flux of string. Find IDs returns a flux of string on which we would do a flat map. For each individual ID, we would perform a reactive request. Make request here returns a mono of string, for instance, or a mono of response. So we get what we actually get is a flux of response at this point. So each response we could map to a value object. For instance, if we get some JSON, we can extract the body of the response and turn that into a business object. And last, we could collect all the values that we got into a list. So we at the end we get a mono of list of value by doing this set of steps. But it's all declarative. At this point, nothing has fired on the network, right? You have to subscribe to this mono. This mono is representing your processing pipeline, but you have to subscribe to it to actually trigger the pipeline. So we will need to subscribe to the results mono. And what that gives us, even with this very shorthand version of subscribe, what that gives us is a disposable instance, D. And the way that we can cancel our whole pipeline is by simply calling d.dispose. So if you fire up this complex request, you actually declare a complex set of steps. And when you subscribe to it, you trigger the pipeline. And if it takes too long, then you can just dispose the pipeline once, and you're done. So let me get back to the code and show you how I kind of implemented that Here I forgot to show you the blocking request. Blocking request is when you exchange the request. It's actually what I said in my slides, is directly returning the response. So you could get an error via an exception, but that's pretty much it. You cannot cancel it at that point. The simple reactive request, when you exchange the request, you get a mono of string here. I simplified the example, but you get a mono. And by subscribing it, well, in that subscribe way to mono, what I do is I subscribe my mono, and then I use some hooks to update the GUI according to the kind of event that I got. But suffice to say, if you subscribe that, you get a disposable. I can add this disposable to my queue in the GUI, which is tied to this cancel button. And when I cancel the most recent request, what it will do is simply detect that this is a disposable. So if the latest in the queue is disposable, then I just dispose it. And that should, for a simple case, that will obviously cancel the request, but for a more complex case, that should propagate to all the steps and also cancel in one go, in one operation. So let's try to see that in action. So yeah, I have simple reactive request. And I also have, make complex request here. So I also have this kind of the same spirit of what I just shown in the slide, something where I start with a sequence of IDs. Here I simulate that with a range, and I flat map for each ID. I make an inner request. Here I use a bit of a helper method to tie that to the GUI. And also, if I want to add some operations to the mono, I could do that here. So for instance, if I want to skip some results, or if I want to filter some results, for instance, I can do that here. So if I only want the results that contains the string 3, I can do that like so, and that will become useful in the next demo. But yeah, as I said, collect list, and I can represent the whole result, the set of results as a string. And again, I add to my work queue, and what I add is something that like the disposable that I get when I subscribe to this complex request. So here I have flux selected. I can do simple request here for the purpose of the demonstration. Okay, it's done. I can cancel the mono. Pretty easily. And if I do complex requests, you'll see that it will trigger actually five requests. Okay, that each take about 3 seconds. So what if I want to cancel it? Yeah, in one click, I actually canceled the whole stuff. Okay. So yeah, the first thing that we get from that is that cancellation in reactive streams, in reactor, in mono and flux, is definitely a first-class citizen. Oh, sorry. I need to kill the app. Yeah. So yeah, it's cancellation is definitely a first-class citizen, and it propagates all the way. So when you compose a reactive pipeline, you can add many operators, many steps, etc. At the end, it's always represented as either a mono or a flux. And once you activate the pipeline, once you subscribe to this mono or this flux, you always get a disposable, and you can always use that to cancel the whole pipeline, right? So that's a pretty important point. And we saw that for completable future, for instance, that was not the case. If you add a step to your completable future pipeline, say by using when complete or then async, etc., etc., the inner steps, the steps that came before, represented as future, they don't get necessarily notified of a cancellation. Okay. So now we've seen cancel. I'd like to talk about timeouts now, and have a look at the classic solutions that we have for timeouts. So most of the time, when you look at an API that has some notion of latency baked in and allows you to set timeouts, such an API will allow you to set timeouts by providing a maximum duration. For instance, if you have a budget of 5 seconds for your request, you could call your client with this method, and you would need to pass 5 along, so 5 and a time unit seconds. But passing a maximum duration doesn't compose and lacks abstraction. Often it's too fine-grained to be useful to users. Think of the complex case. If you have multiple, if you are coding from a higher level abstraction and you have multiple steps involved in your processing, and you want to put timeouts on the whole user interaction, but really the library that you use to make requests only lets you set timeouts for individual fine-grained operations. So you would have something like that. I have a budget of 5 seconds to do three operations. First operation is to make a request on URI 1. Second operation is to make a request on URI 2. And then maybe you want to write on a file or something like that. The problem is you have the opportunity to set the timeout on each of the discrete steps, but what you're interested in is a big timeout around all that stuff. So yeah, timeout is not gonna cut it, because even if the requests here are asynchronous, what if one takes like the whole budget? Or what if one needs the result of the previous one and takes close to 5 seconds? Like the first takes 4 seconds and the second one takes 2 seconds. Combined, they take up to 6 seconds, but the timeout won't trigger. So we need a different solution. Another solution is to pass a deadline around. So instead of passing the timeout, you pass a timestamp. So my budget is 5 seconds. I pass the timestamp of now plus 5 seconds. So we can see that if we have multiple small discrete steps, by passing the same deadline to all the steps, they become constrained by the same deadline. So we wouldn't have the same issue as we had with the timeout. So it composes well, but it leaks into the API. in the sense that now it's up to the caller, the user, to compute the deadline and to get the notion of the deadline. He has to do boilerplate conversion and passing around the deadline at every level. So if we were to extract this into a method, the process method would force you to call it with a timestamp, a deadline, and then pass the deadline to each individual step in the recipe, basically. So it's up to the user to compute the deadline. And most of the time, the user doesn't really care about the notion of a deadline. It just says, I have a budget of 5 seconds, right? So it's less practical. What about reactive programming? So in reactive programming, this would look like a perfect case for the timeout operator. Let's see how we can apply that. So again, we have a mono. Here we have a simpler mono of void. Our process is represented as making a first request, then making a second request, then writing to a file with an asynchronous wrapper. It's probably not the best example, writing to a file, but anyway, the whole process is made up of 3 steps, and then it's represented as a mono of void because it doesn't hold any result. It's just, we are just interested in whether or not it completed successfully. And then we can subscribe to this process, and we get a disposable for manual cancellation. So if we want to turn that into something with 5 seconds budget, we can simply add the timeout operator in the middle just before subscribing. And even though we might have constructed this process, this mono void from an external library, we can apply, since we get a mono, we can still apply further operators, including timeout. And by just doing that and providing a duration, we ensure that the whole operation will take no more than 5 seconds. And yeah, as I was saying, we still get a disposable, so we still could manually cancel it before the timeout, for instance. So we get ease of use with duration, but something that is composable and fine-grained by having the capabilities of Mono and Flux APIs. If I go back to the Mono of list of value example from before, the one that I dubbed the complex request scenario, we had this flat map inside of which we were making a request. And we also got a single disposable that represents the whole pipeline, and that we can use to cancel the whole pipeline. So we can add a timeout on the whole complex operation, like the five requests firing in parallel. We can put a timeout on that. But we can also put a timeout on each inner request. So if with a smaller timeout, for instance. So if any of the inner requests takes more than 1 second, it will get cancelled, basically. And then if the whole operation takes more than 5 seconds, it will also get entirely cancelled. So we can see that with reactive programming, again, we describe a complex processing pipeline, and we can at the last minute add a notion of a timeout on top of it. And then if it takes too long, then the timeout triggers and it basically destroys the whole thing. And then you, as the user, you'll get an error, a timeout exception, basically. So let's see that in action. So let me go back to my complex request example in the app. So here I can demonstrate the inner timeout. So I can say, okay, I use flat map delay error, so it has the side effect of delaying the completion, like the failure of the whole operation until each inner request has had at least a chance to run its course. But if we do for the inner request, if we do just add a timeout here and say the duration is actually depending duration dot of seconds of I. By doing that, we can see that if each request takes about 3 seconds to run, we can see that only the first and second inner request would time out. So the first inner request has ID 1, so I equals 1. Then the second I is equals 2, etc., etc. So the timeout for the first is of 1 second. The timeout for the second inner request is of 2 seconds. The timeout for the third inner request is of 3 seconds, and 4 and 5 seconds for the other ones. So only the first two should time out. Let's check that. It will take a bit of time to start. That's due to Zoom, unfortunately. Okay, so if I click on complex request, it will trigger this code. So it will trigger the range of 1 to 5, flat map into 5 inner requests that are represented by 5 progress bar. But now some of these, yeah, we could see that briefly. Some of these will time out. So since we have a timeout of 3 seconds for the third inner request, sometimes we get a bit of a hiccup and it actually times out. Sometimes it completes just right right on time. But you can see that when I run the complex request scenario, generally the first 2 requests will error with a timeout exception that says didn't observe any item or terminal signal within 1,000 milliseconds, so 1 second, respectively 2 seconds. Okay. So what if I want to? So this one is a bit less. I couldn't make it graphical in time, but I could also imagine I can do a timeout here and say duration of seconds 2, for instance. What if I do that, right? Oops. So now I have an inner timeout and an outer timeout. So the outer timeout should logically cancel all 5 inner requests. Oh, and by the way, I can actually cancel the whole thing still, right? But yeah, let's see how it behaves. That's interesting. We got cancelled. So this is the inner timeout in action, but that is what I was talking about. It's not entirely adapted to the graphical UI that I coded. I didn't have time to adapt that case. But basically what happens is when that timeout, that outer timeout occurs, downstream, what you'll see is an exception. So I can log that in the console. What you see is an exception, but actually upstream, these operators, and including the flat map and the inner request, they will all get cancelled. So when the timeout triggers, it cancels the source, which in turn propagates this cancellation to all of the components. And when that inner request object, the declarated inner request object receives the cancellation, it will update the GUI. So it doesn't show as an error; it shows as a cancelled status. But it's still a good demonstration, I think, that you can apply a global timeout of 2 seconds, and it will clearly cancel the individual steps. All right. Okay. And final topic, what if I want to retry? Retry on what? You could retry on several things, actually. You could retry on remote failures in your request. You could retry on timeouts. So what if I want to combine with timeouts? Maybe you can see how it's starting to get fishy with completable future, the code that we had before, if I want to add a notion of retry. And even then, when you retry and you have a complex request, well, you want to keep the whole thing cancelable. And maybe you want to apply more advanced strategies, like apply an exponential backoff. By that, I mean, if you have a complex request that performs several requests, inner requests to multiple servers, or to the same server, but if there is an error that is due to you over or multiple users in parallel overwhelming the server, but you apply a very simple and naive retry strategy, which is to retry immediately, you're going to have problems, because then you are overloading the server once and then immediately triggering the same request again, which is bound to make things worse, right? It's if the server was already overwhelmed, then it will be on fire now. And even if you do apply a delay in your retry, like you give a few hundred milliseconds to the server to recover a bit, if it was overwhelmed because a lot of users at the same time sent a request, then maybe if all of these users came at the same time, and how do you say? Yeah, all of these users came at the same time, and then they retry after a few hundred milliseconds, but the same number of milliseconds, then they will request the server again at the same time, and it will cause the same error conditions. Basically, it's a retry storm, right? It's so you want to apply exponential backoff with jitter and advanced strategy. How do you do that with with Future, you would have to code a lot of boilerplate to achieve that. But with a reactor, you just add a single operator. So back to our complex example. Instead of, well, in addition to the timeout, now we add this retry when operator. So we use the retry when operator. We define that we want a backoff style of retry. We want to retry at most 5 times. We want a minimum delay between retries, between attempts of 10 milliseconds. We also want the delay to grow exponentially up to 1 second maximum. And to avoid the retry storm problem, we'll define a jitter. So some randomization of the delay up to a certain % of the initially computed delay. So it will add some random number of milliseconds to the delay of each client. So we don't get into the situation where a fleet of clients that overwhelm the server retry at the exact same time, basically. So by doing that, we retry on remote errors only. So a server is unavailable or 500 type of error, for instance. We still have something that is manually cancelable. We still are able to apply a timeout on the whole operation, including the retry. So position matters when you use the operators, right? So here we do a retry with a global timeout. But if we were to reverse the 2 operators, we would get a timeout of 5 seconds on each attempt, and then up to 5 attempts at performing the request. So yeah, it can be a bit different, right? So let's see that into action. So if I do this, so duration of milliseconds, max backoff, max backoff duration of seconds, and some jitter. There's already some jitter defined, but I can follow it, the example, and set some. Okay, let's pretend it's all smooth. Okay, so now I have a timeout on the whole operation, but on each attempt, right? And then I will retry up to 5 times, which will always fail, but we should see some repetition of the requests. So yeah, that's going to be the last demo of this talk, but that's pretty much what I wanted to show, is that these concepts of timeout, cancellation, well, by having cancellation as a real first-class citizen in reactive programming and in Reactor, we can get to a state where timeouts and retries are really integrated into the library. And of course it fails. Okay, let me do something a little bit different. Let me put the retry actually on the inner request. Okay, and let's tune that down. Yeah, we can keep it 5. Okay, so we could observe some interesting behavior that the first 2 inner requests that do timeout due to that I here, they get retried. They get retried more and more with more and more delay, basically. So yeah, that's a way to visualize that we were able to apply the concept of retrying to our inner request pretty easily. Of course, if I reverse the 2, there won't be an error, so the retry won't happen. The retry is actually triggered by the error signal, but we could do something different, like a repeat or something like that. But yeah, I think that's an interesting demonstration of this concept. Well, that's all for me. I hope that I was able to convey this idea that cancel, retry, and timeouts are very important in a world where you have asynchronous processes, and by using reactive programming, you get a more integrated experience and a better experience overall. That if you were to do the same thing with completable future, for instance, or future in general. I hope that you learned something, and that's all for me today. If you have questions, you can join the dedicated Zoom meeting that will be shared in the Slack channel that corresponds to this session. So be sure to search for the Slack channel, and then you can ask questions there or join the Zoom meeting. And otherwise, you can reach out to me on Twitter at Project Reactor for the project, the whole team, and at Simon Baslam for my personal Twitter handler. Thank you.
Thanks so much, Simon. That was great. If any of you have questions for Simon, we have a Q&A session starting now. Click the Zoom link on the breakout session page to join. The next breakout session will begin in 5 minutes. So take a break, stretch your legs, and we'll see you all soon.